The universe is a blend of two extremes and is all about balance. Lao Tzu, an ancient Chinese philosopher, called it yin and yang. Newton summed it up as every action having an equal and opposite reaction. These opposing forces keep things balanced, and when that balance or equilibrium breaks, creation happens.
The universe started in this one primordial explosion.
According to the Big Bang theory of origin, the universe was formed from the stage of nothingness, since there was no concept of time available before the Big Bang for any known matter to even exist. To keep the energy of the universe constant and not violate the law of conservation of energy, the Big Bang nucleosynthesis should have created equal amounts of matter and something called antimatter in the early universe. But today, everything we see, from the smallest life forms on Earth to the largest stellar objects, is made almost entirely of matter. Comparatively, not much antimatter is to be found. Now the question is, what is antimatter? Antimatter is like the evil twin of matter. Same mass, opposite charge. When they meet, annihilation happens, releasing energy in the form of photons, gamma rays, and neutrinos. So, if the Big Bang did create equal amounts of matter and antimatter, and if everything was perfectly balanced, then everything would have been completely annihilated, leaving behind just radiation and no trace of matter at all. But clearly matter exists because we see it around us. So, what exactly tipped the scales in favor of matter? And why did matter win over antimatter? Let's find out more about one of the biggest mysteries of our universe, Matter-Antimatter Asymmetry. My name is Siddharth and you're watching The World of Science. In the early moments of the Big Bang, a very tiny imbalance led to more matter than antimatter. For every billion matter-antimatter pairs, there was one extra matter particle. This process, known as baryogenesis, is the most accepted explanation for this asymmetry. So then, what exactly caused this one extra matter to appear? Noether's theorem tells us that every symmetry in physical systems has its corresponding law of conservation. Whenever this symmetry breaks, the energy levels of the system shift, creating new particles or fields. For particles like baryons, such as protons and neutrons, and leptons, such as electrons and neutrinos, the conservation laws present are called baryon number and lepton number respectively. Baryon number can mathematically be expressed as 1/3 of the difference between the number of quarks and antiquarks. For example, in protons, the number of quarks are 3, antiquarks 0, so the baryon number is 1. For each particle to preserve symmetry, the baryon number and the lepton number must be conserved. But then, what are these symmetries? Three fundamental symmetries apply to all physical systems: C, charge symmetry; P, parity symmetry; and T, time symmetry. Any physical system containing a particular particle will yield the same result if, number 1, that particle is replaced with its opposite charged counterpart; number 2, its mirror image is reversed, which by the way we call chirality; and number 3, the physical system is run in the inverted direction of time. Take for example a system with an electron, which would show similar results to a system with a positron, spinning in the opposite direction and time reversed. A positron is basically the antimatter counterpart of an electron. This combined CPT symmetry is very well maintained in classical mechanics. However, in quantum field theory, things get a little weird and this symmetry can break down. So something unusual happened in 1957. Physicists Changdao Li and Shen Yang observed violations of the C and P symmetry separately during the weak force interactions among particles. However, when the same C and P symmetries were applied together, there was no violation. Everything remained intact, but not for long. So in 1964, physicists James Cronin and Val Fitch observed a combined CP violation during the decay of a particle known as a kaon. A kaon can decay into its antiparticle known as antikaon by transforming a down quark into a down antiquark. And similarly, an antikaon can decay into a kaon by transforming a down antiquark to a down quark. Now in quantum mechanics, we deal only with probabilities of events happening. and thus we can find the probabilities of two decays happening simultaneously. For CP symmetry to be preserved, both decay processes have to have equal probabilities, and this is where Cronin and Fitch observed differing probabilities. This is called CP violation, and it means that the universe doesn't treat matter and antimatter equally. Without CP asymmetry, the Big Bang would have created equal amounts of matter and antimatter, which would all have annihilated, leaving behind an empty universe with only radiation left behind. Recently, in 2022, results from the Large Hadron Collider Beauty experiment on CP asymmetry showed the largest matter-antimatter asymmetry ever observed, the ratio of which was almost 7:1. Physicists are keen on finding the reason for this. Researchers have observed spontaneous transformations between particles and their antiparticles occurring millions of times per second before they decay. Scientists think that some unknown entity could have intervened in this process during the early universe that might have caused these oscillating particles to decay more as matter than antimatter. So by that logic, if the possibility of antichaons transforming into kaons is much greater than kaons transforming into antichaons, then naturally there will be an abundance of kaons over antichaons, similar to what we see for matter in our universe. This scenario is not limited to kaons. Since 2000s, CP violation has been observed in particles like B mesons and D mesons. These instances of symmetry breaking could possibly explain the asymmetry between matter and antimatter. In addition to baryogenesis, another phenomenon called leptogenesis is used to explain baryonic asymmetry. Neutrinos come in a range of masses, and they can be left-handed or right-handed based on their chirality. So then, according to this hypothesis, during the early hours of the universe, there was the presence of mostly heavier versions of neutrinos, and these neutrinos likely decayed more often into antileptons than leptons. These antileptons could have undergone a quantum tunneling process to reach a higher energy state, transforming into baryons and adding to the matter count. Thus, leptogenesis along with baryogenesis could have increased the amount of normal matter in the universe. Another possible explanation for this is that matter and antimatter both are essentially separated into different, widely distant regions of the universe. The formation of antimatter galaxies was originally thought to explain the baryon asymmetry, but from a distance, antimatter atoms are indistinguishable from matter atoms, and they both produce light the same way. Along the boundary between the matter and antimatter regions, however, constant annihilation and subsequent production of gamma radiations would be detectable. Such boundaries, if they exist, would lie deep in the intergalactic space, and the density of matter in the intergalactic space is reasonably well established to be 1 atom per cubic meter. Now, assuming this is a typical density near a boundary, the gamma ray luminosity at the boundary interaction zone can be calculated, and that in turn will help us locate the antimatter galaxy. But based on analysis, it is now deemed unlikely that any region within the observable universe is dominated by antimatter. What's more interesting is that these are not the only theories that explain matter-antimatter asymmetry. There are so many more theories, including the one that proposes the existence of an anti-universe made up of antimatter where time runs backward. We have explained anti-universe in great detail in this video. Matter-antimatter asymmetry is one of the most complex problems in modern physics yet to be solved. So what do you think about the matter-antimatter imbalance in the universe? Let us know in the comments. If you found this video interesting, please leave a thumbs up and share it with your friends. Make sure you subscribe to the World of Science because it matters. Until next time, stay scientific.